Hello aviators, Captain Dwight with you. Today we're going to continue our discussion of aerodynamic forces. It's going to be a little bit technical. Today the discussion is on the theories in the production of lift. Now don't get a big headache over this. There's about 8 pages in your PHAC book that get into these theories in detail. It's not something that you're going to need to know all the details, the nuances, and all of that of these 3 theories. Basically what I want you to know is the name of the theory and just a brief description of what it is, how it works. There's only one question in the test database for your private pilot exam that deals with this. So it's not that difficult. All you need to know is the name of the principle and what it does. Basically, all of these things describe lift in this manner. With an airplane wing, we get a pressure differential beneath the wing compared to above the wing. Basically, we get high pressure below the wings, low pressure above the wings. So that high pressure, in effect, is pushing up on the aircraft, and the low pressure on top, in effect, pulls it up. So that's what gives us lift. So this first theory we're going to look at is the Magnus Effect.
The Magnus Effect helps to explain the theory of lift. German physicist and chemist Heinrich Magnus made some experimental studies of the aerodynamic forces on spinning cylinders. If air flows against a cylinder that is not rotating or spinning, the flow of air above and below the cylinder is identical and the forces are the same. However, he noted something. If the cylinder is rotating, the flow is changed. This is due to 2 factors: viscosity and friction. Viscosity is the property of a fluid that causes it to resist flowing. Ketchup has more viscosity than water, which is apparent when you try to get ketchup out of a bottle. It resists the flow. However, water and even air also have viscosity, and they too resist flow. Friction is the second factor at work when a fluid, including air, flows around a rotating cylinder. Friction is the resistance one surface or object encounters when moving over another, and exists between a fluid and the surface over which it flows. So, looking at a rotating cylinder, you can see that the flow moving over the top of the cylinder is moving faster than the air under the cylinder. This is because the cylinder is rotating and the air is going with the rotation on the top and against the rotation on the bottom. So that resistance of flow is reduced when the cylinder is spinning in the same direction and increased when the cylinder is moving in a direction opposite the flow of the air. So the increased velocity of the air moving over the top will have lower pressure than the slower air under the cylinder. Now you'll also notice these 2 stagnation points here, A and B. Notice how they are below the center line of the cylinder. What we have now is we have upwash ahead and downwash at the rear. The low pressure areas produce an upward force known as the Magnus Effect. Take a look at this wing. Notice where the stagnation points occur, A and B. Air circulation around an airfoil occurs when the front stagnation point is below the leading edge and the aft stagnation point is beyond the trailing edge. Now, this Magnus Effect we don't really need to know in detail. Whenever the Magnus Effect is brought up, all you really need to think of is a baseball, for instance, and how a pitcher can throw a curveball. It's really airflow going around a spinning ball or a cylinder, and that causes pressure differentials, higher pressure against the spin and lower pressure going with the spin.
Okay, the second theory in the production of lift that we want to discuss is Newton's third law of motion. Now, you've all heard this one. For every action, there's an equal and opposite reaction. Well, let's see how this works with a wing. We have a wing right here, as you can see, and we've got the relative wind coming along, hitting the wing. Some of the air shoots over. Now what happens is this wind hits the bottom surface of the wing and is deflected downward. So, Newton's third law, for every action there's an equal and opposite reaction. The wind hits the wing and is deflected down. Well, that means there has to be an opposite reaction to the wind going down. Well, the wing gets deflected up. Also on the top, you notice here that this wind is being deflected downward on the top too. So again, Newton's third law, for every action there's an equal and opposite reaction. Wind being deflected down, when the wing is going to be deflected up. So that one's pretty simple. Just remember, Newton's third law of motion deals with, for every action there's an equal and opposite reaction. And finally today we're going to discuss Bernoulli's principle. Let's take a look at this with this hairdryer and a ping pong ball. Okay, you notice the ping pong ball staying right into the airflow. Look what happens as I turn it to the side. You would think that the gravity would pull it down, but the ping pong ball just stays right there in the airflow. I can get a pretty good turn on this thing. Go back the other way. And you see it's a pretty severe turn of bank before finally it pops out of the airstream.
Take a look at this drawing. We have our hairdryer here shooting out air at a pretty fast speed. Of course, the surrounding air isn't moving at all. Now, according to Bernoulli's principle, when you get air flowing faster or liquid flowing faster, that decreases the pressure. So we have decreased pressure in this area that's flowing. The higher pressure out here, of course, wants to equalize. And so it's trying to get in, and in fact what it's done is almost put up an invisible wall here that's holding our ball in. So that's the concept, the science behind the hairdryer experiment.
So, how does that work? Well, Mr. Bernoulli found out that fluid going through, let's say, a tube in this direction and comes into a narrow portion, that what happens is that the fluid will speed up here. The velocity of the fluid will speed up and then slow back down here. Well, we have a certain velocity here, and along with that, we have a pressure reading. And what Bernoulli found out is that as the velocity increased here, the pressure decreased, giving us a lower pressure scenario inside this, right in this section here. And then, of course, when it came back out, the velocity slowed back down to match over here. The pressure increased to match here. So that's the basics of it. As it goes through the narrowing portion there, you get a pressure differential, a pressure decrease. So, how does that work with a wing? Well, let's take a look. If I take off this part right here, does that not look like the top half of a wing? So our air coming along here has to be narrowed, going over the top of the wing, than it does, don't have this drawn very well, over the bottom of the wing. So according to Bernoulli's principle, since this air speeds up, we have to get a pressure decrease on top of the wing. Bernoulli's principle seems to be the predominant theory in the production of lift. And I think if you know Bernoulli's principle, you won't have any trouble with the written exam. Aviators, fly safe.